In today's video, we're going to introduce another reaction of dienes called the Diels Alder reaction. The Diels Alder reaction is a 4+2 cycloaddition. And it gets that name from having a diene that has 1, 2, 3, 4 carbons, and an alkene that has 1, 2 carbons. As you can see, the Diels Alder reaction has two components. The first one is known as the diene. The second one is known as the dienophile. And it reacts like this. One of the bonds in the diene attacks the dienophile, which gives electrons back to the diene, and then another arrow to move that diene or that alkene 1 carbon over to give cyclohexene products. This is a cyclohexene. If we were to number our carbons, 1, 2, 3, 4 carbons came from the diene, and 1, 2 carbons came from the dienophile, and there is now a carbon-carbon double bond between carbons 2 and 3 of the diene. Most of the reactions we've looked at up to this point have not needed us to talk about molecular orbital theory to understand how they work. And we could use electrostatics and partial positive and negative charges to explain them. But there are no charges necessary in the Diels Alder reaction. And so for this, we're going to have to consider some molecular orbital theory to understand why it works. And so the first thing I'm going to do is consider the molecular orbitals of the diene, and specifically the pi bonds in the diene. There are 4 carbons, and so there are going to be 4 p orbitals that overlap to form this diene. And the most stable structure has all of those regions lined up, or all of the phases lined up with no nodes in between them. The next highest energy orbital has 1 extra node, and it comes between carbons 2 and 3. There. The third one has 2 nodes. The first one comes between carbons 1 and 2. And the next one comes between carbons 3 and 4. And the highest energy orbital has 3 nodes, 1 between each p orbital. Here, and so I've oriented these in order of energy. So the highest energy orbital is up top, the lowest energy orbital is on the bottom, and there are 4 pi electrons. The first 2 are going to go in this orbital down here, and the next 2 will go in the second highest energy orbital. And so everything below that dotted line is occupied, and this is the highest occupied molecular orbital, or the HOMO orbital. And everything above this dotted line is unoccupied. So orbital 3 is the LUMO, or the lowest unoccupied molecular orbital. If we consider the molecular orbitals of the alkene, it's got 2 because it's got 2 carbons with p orbitals on them. The first one has no nodes. This one is occupied. The second one has 1 node between the 2 atoms, and this one is unoccupied, making the lowest energy orbital the HOMO, and the highest energy orbital, the LUMO. In order for a bond to form, you have to have the highest occupied molecular orbital of one structure interacting with the lowest unoccupied molecular orbital of the other. And so for the Diels Alder, we're considering the HOMO of the diene with the LUMO of the dienophile and the LUMO of the diene with the HOMO of the dienophile. And these work because the phases line up. So if we were to orient this diene in a different configuration, like this, where this is carbon 1, 2, 3, and 4, and this was carbon 1, 2, 3, and 4. Carbon 1 and 2 have shaded phases on the bottom, and carbon 3 and 4 have shaded phases on the top. So that's the HOMO of the diene, and it's going to interact with the LUMO of the dienophile. If we number these, carbons 1 and 2, carbons 1 and 2, carbon 1 has shading on the bottom, carbon 2 has shading on the top. And so notice that these shaded phases are lining up and the unshaded phases are lining up. So those phases match and they're going to overlap. If we look at the LUMO of the diene, again, we're going to number our carbons 1, 2, 3, and 4. And shading carbon 1 was shaded on the top, carbons 2 and 3 were shaded on the bottom, and carbon 4 was shaded on the top. For the alkene, again, I'm going to number my carbons 1 and 2. They are both shaded on the bottom. And so the HOMO of the alkene also overlaps well or matches shading of the LUMO of the diene. In order for the Diels Alder reaction to occur, the diene has to be in what's called the S-cis transformation. And so let's see what that is. We're going to start with an S-trans conformation. And that's when the diene is oriented like this. So the S part of this comes from the carbon-carbon single bond, or the sigma bond here. And the diene is oriented trans across that carbon-carbon single bond. And so this is the S-trans conformation. The S-cis conformation then looks like this, where the two alkenes are on the same side of that carbon-carbon single bond, and so it's cis. And in order for a Diels Alder reaction to occur, it must be in the S-cis conformation. Because this is a concerted reaction, when an alkene comes in, this all happens at once. And if it's not in the S-cis conformation, carbons 1 and 4 aren't close enough to one another to undergo this reaction. And so we get a product that looks like this, where the bonds in green are new bonds formed in the Diels Alder reaction, and the bonds in red and blue were there before. If we look at a couple of examples, this first one, the diene, is held in the S-cis conformation because it's in a cycle, and so this occurs very fast. Again, electrons go from the diene to the alkene, and then the alkene donates electrons back, and we have one more arrow that pushes across. And this is going to give us a weird looking structure. It's a bicycle. It looks like this. This can be hard to draw, and so another way you can draw this structure this is just the standard cyclohexene, and carbons 1 and 4 were connected through carbon 5, and so we have carbons 1, 2, 3, and 4, and there was a fifth carbon in between there. This is carbon 5. Over here, this is carbon 1, 2, 3, 4, and 5. In this bottom conformation or bottom example, there's no reaction. This diene is locked in the S-trans conformation, and so it cannot undergo a Diels Alder reaction. So far, we've looked at Diels Alder reactions that didn't have any substituents on them. Now I want to look at a couple of examples that have substituents on them. And so a couple of notes: electron withdrawing groups. So electron withdrawing groups on the dienophile increase reactivity. And so if we look at an example, the diene, we're just going to use a standard 1,2 or 1,3-butadiene plus a dienophile. I'm going to put a couple of electron withdrawing groups on here. So this ester, these are both ester functional groups here, are electron withdrawing. This oxygens, both of these oxygens are all electronegative, so they're withdrawing electron density. You've also got some resonance that can happen when this pair of electrons goes up there and that pair of electrons goes there. You generate a resonant structure that looks like this. Which makes this carbon down here more electropositive. And so this is an electron withdrawing group. I'm going to get rid of this now. So this makes this reaction much faster. And again, this pair of electrons is going to donate to the dienophile. And so the reason why electron withdrawing groups make this a faster reaction is the first part of this reaction that happens is the diene attacking the dienophile. We want the dienophile to have a slightly positive charge so it can accept electrons. And then the dienophile gives back electrons, and that moves over, and we wind up with a cyclohexene with two substituents hanging off of it that are esters. If we consider the diene electron donating groups, increase their reactivity. And so if we take a look at this diene, I'm going to stick a methoxy group on here. And remember that while oxygen is an electronegative, when it's connected to carbon with an alkene, it's an electron donating group through resonance. So I can, have resonance here by kicking those electrons down, and I form this resonance structure. And so that makes this an electron donating group. And electron donating groups on dienes make the Diels Alder reaction much faster. I can donate those there because this carbon here is now got a little more negative charge on it. It's got a partial negative from here. And so it donates those electrons faster, which increases the reactivity of this diene in a Diels Alder reaction. And we wind up with this cyclohexene product. So far, we've looked at mostly symmetric Diels Alder reactions, but what happens if you have an unsymmetric Diels Alder reaction, like the one shown here? In this one, the product could be drawn sort of as we see here. This goes here, there, and we wind up with this product here. Or the alkene or dienophile could have been oriented the other way, like this. And so we wind up with this product. In order to understand which of those products is more favored, we have to consider resonance. So you have to consider resonance. For the diene, we have a resonance structure. It looks like this. If I take these electrons and kick down, those come across, and that goes there. We wind up with this resonance structure. For the alkene, we've got electrons that can be pushed up there and there to generate this resonance structure. The favored product is going to be the product that matches a negatively charged atom with a positively charged atom. And so in this case, carbon 1, 2, 3, 4 is going to wind up being bound to carbon 1, 2. So this is going to wind up favoring, this is the major product, where this is carbon 1, 2, 3, and 4. And this is carbon 1 and 2 of the dienophile. And so we wind up with a bond between carbon 4 of the diene and carbon 2 of the dienophile, because carbon 4 had a negative charge and carbon 2 had a positive charge. Because Diels Alder reactions are concerted, they are stereoselective. And so all this happens at once. It's a concerted mechanism. This is stereoselective, and it's going to preferentially form this product. Similarly, this reaction, again, is concerted, is going to preferentially form this product. And so a cis alkene forms a cis ring product. And a trans alkene forms a trans cyclohexene. When you start off with a cyclodiene, there are two potential products you can form. The first one is the endo product, and that occurs when the substituents that you're attaching on the diene are under the ring that you form. And the exo product occurs when the substituents that are attached to the alkene or the dienophile are outside the ring that you form. These conformations or structures can be very difficult to draw, and so an alternative to drawing them, as shown here, is to draw them more like you're used to drawing structures and using wedges and dashes to show endo and exo. So in the endo product, the substituents are on the opposite side of the cyclohexene as the bridge that was there before. And so my bridge, I have drawn up. The bridge is carbon 5. It's up. It's here. Let's skip 2. The bridge is up, and so my substituents must be down. And so I'm going to use dashed wedges to show them. In the exo product, the bridge is up, and the substituents are up. And so if I draw that one, it might look like this. Where this is carbon 1, 2, 3, 4, and 5. If the dienophile has substituents with pi electrons, it tends to favor the endo product. So in this example, this is the dienophile. This has pi electrons. I expect the endo product to be the major product because it has pi electrons. If the dienophile does not have pi electrons, the exo product tends to be favored. Look at a couple of more examples. This first one, the dienophile has some pi electrons, and so the endo product is going to be favored. We draw the mechanism, it looks like this, remember? And the product then looks like this. Where the substituents are going down or under the new cyclohexene. Alternatively, you could draw it like this. Where my bridge is coming up and the substituents are going down. These are both the endo product and they are favored. If you look at the second example here, the dienophile does not have any pi electrons in it, and so likely the exo product is going to be favored. The mechanism looks the same, but the product is slightly different. Exo product has the new substituent on the outside, like that. This is a 6-membered cyclic diene, and so if we number these carbons, 5 and 6 form the bridge, and so we have carbon 1, 2, 3, 4, 5, and 6 are up top here. If we draw it like a little bit more like we're used to, it's going to look a little bit like this. The bridge is going up, and so my substituents must also be going up. And so I'm going to draw everything on wedges. Again, if I number my carbons, this is 1, 2, 3, 4, 5, and 6. And so because it has no pi electrons in the dienophile, this is likely going to favor the exo product. That's going to wrap up today's video. We'll pick up with some more examples in class next time.